Our next talk, you are in South Seas CDF. Our next talk is Critical 0 Days, Remotely Compromise the Most Popular Real-Time OS with Ben Seri and Zusman.
Hey guys, thank you. Thank you for that introduction. Yeah, so my name is Ben Seri. I'm the VP of Research at Armis. And today with me is Dor Zusman, who's a researcher on my team. Dor. Hey. Also in the crowd, we have Greg Vishnipolsky, which is also part of our research team and is a big part of the research that we are presenting today. Armis is an agentless IT security company which is focused on securing IoT devices and unmanaged devices in both enterprise, industrial, and medical organizations. In the last year, we've noticed a particular brand of real-time operating system that is extensively used by industrial and medical devices. So we decided to take it apart and see if we can find any interesting vulnerabilities in it. This research resulted in the discovery of 11 critical zero-day vulnerabilities in the TCP/IP stack used by this popular real-time operating system named VxWorks. So we're going to start a bit about VxWorks, just where is it used, why is it still very relevant today. Then we're going to cover a bit the history of vulnerabilities in the TCP/IP stack implementations, various operating systems. Then we'll go a bit about the actual findings of our research, the Urgent 11 research, and a technical deep dive on some of the more interesting of these 11 vulnerabilities. Lastly, if we actually have time, we'll show an interesting case study of a hospital bedside patient monitor that we have here today, and we'll attempt to do a live demo of this as well. So going back to VxWorks, what is VxWorks and why should you care about it? VxWorks is a real-time operating system. It is owned by a company named Wind River and is actually used by more than 2,000 device manufacturers as the basis for their device that they manufacture. So Wind River produces the code, the VxWorks software, but then there are over 2,000 companies that take this source code, this operating system, and use it as the underlying OS for their devices. Real-time operating systems excel at being compact and reliable, such that can deliver deterministic timings for various tasks running on top of a priority-based scheduler. These features usually fit well with various embedded devices, and VxWorks is used extensively in many different devices. It is the most popular real-time operating system in the market and actually runs on over 2 billion devices. That's the same number of devices that you would find powering Android or Windows devices. Unlike these operating systems, however, this OS suffers from lack of research. In its 32 years of existence, only 13 CVEs were found affected and are listed by MITRE. Now that number has gone up to 24 due to our research, but it is still under-researched extensively. In comparison, when you look at Android, for example, this OS has more than 2,000 CVEs listed that affected, and it exists for only a quarter of the time. So there is much more research to be done in real-time operating systems in VxWorks specifically. VxWorks is used everywhere. You actually find it in almost every industry, from healthcare to manufacturing, aerospace, even automotives, defense, security, all of these industries use devices that require these types of real-time operating systems, require these types of reliable, compact, and highly reliable systems. It is used by the biggest companies in each of their respective fields. In industrial devices, you'll find it in Rockwell Automation, in Schneider Electric. In medical devices, you find it in Philips and GE, and it's in Siemens. All over the industries, you find really big companies using VxWorks as their go-to solution. And even a famous example of this is NASA, which also uses VxWorks to drive their spacecraft and some of the Mars rovers as well. Okay, so going back to TCP/IP stacks, why are they an interesting subject for research, vulnerability research? So in many regards, they are considered the holy grail of vulnerability research. To find a vulnerability in the core networking stack of an operating system, is really something that can allow an attacker generate a lot of power. This is because a couple of things. First of all, these protocols, the TCP/IP protocols, they go back to the 80s. They haven't changed since. So if you find a vulnerability in the implementation of such protocol, it won't change. The code won't be changed almost at all. So you can bet that the vulnerability you find will remain in the code as well. In addition, the network stack of any operating system will be running inside the kernel in ring 0, so with the highest privileges that you can imagine. And by nature, if you find a vulnerability in the TCP/IP stack, it will be remotely exploitable, right? So it's the network stack of the device. If you find a vulnerability in the implementation of the network stack, you can send packets that will trigger the vulnerability. In the past, there were some examples of vulnerabilities in TCP/IP stacks. Back in the 90s, we had a couple of these that affected Windows devices. You might remember the famous WinUke vulnerability. You had this nice pop-up, you click a button, and it crashed any Windows 95 and NT device. Surprisingly, even today, there are examples of this. Last year, there was this vulnerability in the macOS and iOS from Apple. Again, a denial of service attack that crashed these devices by sending a single ICMP packet, especially crafted one. In most cases, though, vulnerabilities discovered in the core networking stack wouldn't arise to actually being remote code executions. It's a rare case. And there will more often be denial of service, resource exhaustion, all kinds of these vulnerabilities that are critical and important, but not remote code execution necessarily. What we found is actually 6 vulnerabilities that are remote code execution, and an additional 5 that are information leaks, denial of service, and logical flaws. Together, these 11 critical vulnerabilities impact the TCP/IP stack used by VxWorks called IPNET. And this stack is the default built-in TCP/IP stack for VxWorks in the last 13 years, since version 6.5. As I mentioned before, VxWorks powers around 2 billion devices. And our estimate is that these vulnerabilities affect hundreds of millions of that 2 billion total number. Some of the VxWorks-based devices don't have networking necessarily, but the ones that do, the majority of them would be impacted by this. The IPNET stack, like I said, is the default built-in stack from VxWorks. It is now owned and maintained by Wind River as part of VxWorks. Essentially, but in the past, it was actually part of another company, Interpeak, and it was then sold to other real-time operating systems. This is prior to 2006. So in the past, you'd find IPNET in Green Hills Integrity, ThreadX, and OSC. The disclosure process we've done with these vulnerabilities started in March, so it's been a 5-month disclosure process. A very complicated one, I think, in the sense that, again, there are many, many impacted vendors here. And like we saw in the week past, so we published this last week, and since then, actually, there have been many, many advisories like this, companies that come forward and say, we're impacted by this, we're working on a patch, and we're trying to meet, and we are offering some mitigation paths. So we saw this in Philips medical devices, industrial devices from Rockwell and Schneider, and some enterprise type devices like Xerox printers. Another interesting example is the Sonical firewall, a firewall that is based on VxWorks, and that device had actually, or still has, around 1 million of these firewalls exposed to the internet, and you can find them on Shodan. Sonical also released the patch and encouraged, and I also do this, if you're a Sonical firewall user, please go ahead and install that patch, because the exposure there is very real. Okay, so, like I said, we found 11 vulnerabilities, and they are actually throughout various subsystems of the TCP/IP stack. There is one vulnerability in the IP stack. There are various vulnerabilities in the, one vulnerability in the IP subsystem, various vulnerabilities in the TCP subsystem, a couple of in the DHCP, IGMP, and even one very interesting and funny vulnerability in a protocol you might have not heard of called reverse ARP, and we'll touch on that as well. So we won't have time to actually cover all of it. We did publish a white paper, and you're welcome to go and read it. But we are going to touch a couple of these, the most interesting of them. And Dor will start with the IP one, cover that.
Okay, so the first vulnerability that we're going to talk about resides inside of the IP parsing system inside of the IP stack of VxWorks. And in order to understand it, we're going to need to have a little bit of background about IP and IP options and ICMP errors. This vulnerability is especially cool because we can do both things that are cool. The first thing is that this vulnerability resides in the IP layer, meaning that we can send a broadcast packet and attack a whole bunch of these devices with just one packet. And let's dive deep and see how it works. So we all know this. This is the IPv4 header. And right at the bottom of it, you have the IP options field. This field is used to extend the protocol, and it basically consists of a type length value options. Every options implement their own type and then their own data structure inside of the value field. Many of these options were released throughout the years, and we're going to focus on a specific one called the source record routing. So these specific options allow an originating party of an IP packet to determine the destination in which the packet must go through, the route in which the packet must go through to reach the destination. The security implications of it are obviously bad, just looking at what these options should do. And this is why it's a common practice not to allow this IP option on your network. But to our surprise, VxWorks supports this to some degree. So as I mentioned, every option implements their own data structure. And in this case, it's a fairly simple one. You have a pointer which points to the current routing position, and a route data, which basically is just an array of IP addresses that are hops for the packet to go through. So let's see how would a client sending such a packet would look like. First, the client needs to compose the route data, meaning that it has to put inside of the route data field all the hops that the packet must go through, and the last hop obviously being the actual destination. It needs to destine the packet to the first hop, and then set the pointer to the start of the route data. Once a router receives such a packet, it advances the pointer, puts himself back in the list, and then sends the packet to the next hop. This happens successively until we reach the final router, which advances the pointer beyond the route data, and that way when the server receives the packet, he knows that he is the final destination and not just a hop on the way, and he can start parsing the packet. Now the RFC demands that when the server would like to answer a client that sends certain IP option, he would have to use the same route that the packet took in order to reach to it, meaning that he would have to reverse the route data and send the packet back in the same manner, just in reverse. Okay, so there are many cases in which a server would like to answer a client IP packet, and one common one is ICMP errors. Some of you may already know this mechanism. Basically, it's a way for a server to report a network error, networking level error, without having an application layer that handles that error. In this case, you have a client sending an IP packet to a closed port on the server, so no application is there to listen and receive and handle this packet, and the server would like to report to the client that there is a problem inside of the packet and he needs to handle it. So the server wraps the packet inside of an ICMP packet. It's specified that the ICMP type is error, in this case port's unreachable because there is nothing listening on that port, and then he sends the packet back to the server. So as I mentioned, what happens when a client sends a packet with an SSRR option? As I mentioned, the RFC demands that the packet will use the same route back. So when the server will generate the ICMP error, it will have to copy the SSRR option back. This seems like a logical step, but what if I tell you that some of the things that can trigger an ICMP error is actually problems when parsing the IP option themselves? Now copying seems like a good idea? Not so sure. Let's see VxWorks' take on this. So basically, this is a very simplified overview of an IP flow of an IP packet inside of VxWorks IP stack. And you can see that the packet takes the first two stages. The first one is the routing logic, which determines whether the packet is destined for us or needed to be routed. The second one is the validation step. And after both steps, the packet is considered validated and sanitized and can be later passed to the layer 3 handlers. So let's imagine an ICMP echo request has arrived. The first two stages occur. Now the packet is validated and sanitized. And now the ICMP handler would like to generate an echo response. So VxWorks try to be generic and implement one function that creates an ICMP packet. In this case, IPNET ICMP for send. So the ICMP handler will call this function to generate the echo response. But as I mentioned, both of the first steps can fail and generate ICMP errors, and because VxWorks try to be generic, they use the same function. There's a couple of problems here. Of course, the design is kind of bad because this function is not aware which one called her, meaning that it can be called from some branches and still assume the packet is validated. And let's see some of the code. So this some of the code of the function, it just tries to blindly copy all of the IP options to the new ICMP packet. And it just iterates through all of them and copies them. There's a couple of problems here. The first one is that it assumes the packet is validated and sanitized and passed those two first steps, meaning that it trusts the length of the IP option when copying and using that memcopy, which will corrupt memory given a malformed length. There's another problem here that it just goes through every IP option and tries to copy them, which is a problem because in SSRR there is no really logical way to put more than one. And the RFC states so, and this code does not validate it. So you can put multiple malformed SSRR option, and this memcopy will be called with the length, and this will result in a stack overflow inside of the IPNET stack, and we have successfully exploited this bug in order to execute code inside of VxWorks IP stack. Okay, so this was a cool vulnerability, but the next one I think is my favorite. It's really simple and really cute. It's in the reverse ARP protocol. So some of you may ask yourself, what is reverse ARP? You all know ARP, right? You all seen this kind of packet. A client asking the network, where is another client? I want to talk to it, give me the data. Okay, but what if I tell you that you can send a reverse ARP response, saying to VxWorks, hey, this is your IP, and VxWorks responds by saying, okay, and adds the IP to the interface. This is a really weird behavior, and to understand it, you need to know that ARP is basically an ancestor to DHCP, and it was used back in the day to assign addresses to machines. There's no reason for VxWorks to actually support this. It's obsolete many years now. And the problem here is that VxWorks doesn't validate that it actually sends a reversed ARP request before passing and handling a reply. It just sees a reply and says, okay, I must have asked for an IP address, let's add it, which is great. We have used this bug in order to a lot of inside of our research, and most interestingly, there are many devices that had hidden debug features that are binded to a specific IP address. So you can use that to open them pretty easily. Okay, so now I'm going to transfer it back to Ben, that's going to talk to you about some interesting TCP vulnerabilities.
Yeah, thank you. Yeah, so that was two of the vulnerabilities. Again, the IP options, one is the RCE, but we have actually 4 additional RCEs in the TCP urgent pointer mechanism. And we're going to talk about 2 of these interesting vulnerabilities to exploit. So, basic TCP, you have client, you have a server, they want to talk to each other, they do the 3-way handshake, and then they can talk to each other. You want to learn more about that? I recommend reading this nice book. But just for the basic understanding here, I want to just go back about what is TCP window and then about the urgent data mechanism. So we all know the TCP window from the network aspect of it. It allows one peer to send multiple segments, TCP segments, without needing to wait for acknowledgement of each of them. And that's the TCP window on the network layer. But actually inside the operating system, in the implementation of TCP, the TCP window is a buffer inside the kernel that is allocated per TCP connection that saves all the segments that were received in the TCP connection. And once an application wants to read data from this socket, it actually reads from this buffer allocated inside the kernel. So it will call the receive system call with a specified length, and then a portion of that buffer will be copied to the application buffer. So again, the only takeaway from this slide is the TCP window is a buffer inside the operating system. So what is the urgent data mechanism? When you search for TCP urgent data in Google, the first result is a nice answer from Stack Overflow. It says, just don't use urgent data. And the fact is that it actually isn't used by modern applications at all. It's a very ancient mechanism going back to the 80s that was invented to allow one peer to send data inside a TCP connection in an urgent fashion. to allow one peer to say to the other, please process this urgent data before you process anything else in the TCP window that maybe has been received before. So that was the purpose of this, but how was it actually implemented? So actually in each TCP header, in each TCP segment, there is allocated the 16 bits of the urgent pointer, and another bit in the TCP flags, the urgent flag. And the urgent pointer is a relative pointer inside the TCP stream that points to where inside the stream the urgent data sits. And the urgent flag means this specific segment has urgent data in it, and the urgent pointer will point you to where it is. But there are a few questions that are arising just from this data structure. First, where exactly does the urgent pointer point to? Does it point to the beginning of the urgent data, the end of the urgent data, in the middle? Where does it point to? And second, there's only an urgent pointer in this structure. There isn't an urgent length. So how long can the urgent data be? So to answer these questions, let's go back in time to 1981. The first RFC, there is a, 1981, I was -6 years old, and Dorothy was -14 years old, so none of us existed yet. And some guys in the IETF discussed these questions about the urgent data in the non-existent WhatsApp group. And so the first RFC to consider this says, in 1981, says the urgent pointer points to the sequence number of the octet following the urgent data. So it points past the urgent data. Okay, sure, sounds simple enough. However, 6 years later, another RFC comes along and says, no, the last RFC was wrong. The urgent data actually points to the last octet, not the one that's following it. And 2 years after that, another RFC comes along and states the same statement. It points to the last octet, not the one that's following it. So there are these contradictions between the RFCs, and in 2011, the latest RFC to consider this came out and said, okay, I don't know how to square this problem, but let's just say that if both sides of the connection agree where the pointer points to, then they will be able to talk to each other. But it does state that the default implementation in all the TCP/IP stacks until that point in time use the first RFC that says that it points past the last urgent data. Okay, so if you're a TCP/IP stack developer today or in 1987 or anywhere on that timeline, you have to ask yourself, how am I going to implement the urgent data mechanism? Which of the RFCs should I support? And also you need to ask yourself, again, there is the question that we haven't answered yet, what is the length of the urgent data? Actually, this last RFC from 2011 does state that because we don't have an urgent length, the urgent data will always be just 1 byte. So you can see there are these discrepancies in the RFC, and this might cause implementation problems, which we will show in a second. How does the urgent data mechanism work inside the operating system? So if you are a client that wants to send some urgent data, you need to send it inside the TCP stream, turn on the urgent flag, and point the urgent pointer somewhere, I don't know, beginning or end of the urgent data. And then on the server side, you need to see that there is an urgent data in the stream and split the urgent data from the non-urgent data. Then you need to send the server application a signal stating that there's urgent data for him to receive. In Linux, this is SIG-urge. And then the application can call a special receive system call with a special flag message OOB that states, I want to get this urgent data, give it to me. And if we want to receive the regular data, the non-urgent data, it will call the regular receive. So the OS here needs to split the urgent data and the non-urgent data, and it needs to know, depending on what type of receive system call is being called, what type of data to transfer to the server application. And this specific mechanism is what is problematic in VxWorks. Here we can see the function inside the kernel that implements this receive system call in VxWorks. And what this code tries to do is understand, okay, I was called with the receive of x bytes, so I want to copy x bytes from the TCP window to the user space. But if these x bytes contain urgent data, I need to subtract the length field, I need to trim it down so it doesn't contain any urgent data. And this is what happens in this specific field, specific line. So let's understand this specific line. So let's say a user requested to receive a specific length, but this in the TCP window contains urgent data in the middle and non-urgent data before and after that urgent data. So the receive system call wants to trim the length so it doesn't contain any urgent data. So this is done this way. First, it calculates what is the initial sequence number of the TCP window, of the current TCP window. That is done with this two variables. And then it goes to the urgent, that's, we denote this as a sequence start. And then the urgent pointer, in VxWorks, the default is to support this first RFC, so it points past the urgent data. So to get to the beginning of the urgent data, you do this -1. So now you found where's the length that doesn't contain any urgent data. That's good. So, but there are a couple of problems actually in this calculation, and let's see one of them. First of them is the edge case of setting the urgent pointer to 0. As I mentioned before, the urgent pointer is a relative pointer to the current sequence number in the current segment. So the actual variable urgent pointer will be sequence start. If we substitute this in the equation above, we can see that sequence start minus sequence start will be gone, and then we will be left with -1. So length here will be underflowed. And this is important because the length is actually an unsigned integer. So once it is underflowed, it will become a very large number. And so this code tried to trim down the length, but in essence, the length actually became a very large number. And now the application that tried to call receive with 1 byte actually gets the entire TCP window. So if we have this simple code here that tries to receive 1 byte from a TCP connection to a buffer on the stack, the entire TCP window will be copied out of bounds to the application buffer to this urgent pointer bug. This obviously can cause a stack overflow in this specific case, or if this buffer was allocated on the heap, it can cause a heap overflow. Okay, so this was the code of this problem was caused by the urgent 0 edge case. And this specific bug was actually averted in some change of code that was introduced in VxWorks 694. However, there are other problems with this specific line. So we had this urgent pointer problem. We have now other problems, and that one of them is the 5-way handshake, which I consider now. So I said that this line has multiple issues. And actually, all 4 vulnerabilities that we found are some kind of edge cases that we can cause this one line to break. This line has a built-in assumption that the urgent pointer always points beyond the beginning of the TCP window. So one is in front of the other. If that assumption breaks, then this calculation here can underflow. Even without the urgent pointer edge case, it can underflow in other circumstances. There are actually many state confusions that we found that can cause this, these two variables, the connection between them to break. So it's a bit complicated, and I won't have time now to go over it in depth. You can read about it in the white paper, but I do want to give one example of this, which is the 5-way handshake, what we call it. So you all know about the 3-way handshake, and here we have the 5-way handshake. These are 5 packets sent to a VxWorks device that will cause this state confusion in which the urgent pointer and the sequence text, both variables here, will be set at different times. And once that happened, then this calculation before we suck can underflow, and the same problem with length will occur. So the first packet in the 5-way handshake is a SYN packet, a regular SYN, but it has a TCP option in it, an AO option that is malformed. And so what VxWorks will do here is actually allocate the socket object and drop the packet, but it won't close the socket at all. It will really leave it open. Now the attacker can send another packet, a fin-SYN urge packet. That doesn't make any sense. But that packet will eventually also be dropped. But it will, in the process of being processed, it will set the urgent pointer relative to the sequence number sent in this specific packet. So now we set the urgent pointer. Again, the packet was dropped, so we didn't get any SYN ACK. So the attacker can send another SYN packet. In this packet, he will say, this is a regular SYN, but he will state another sequence number for the initial sequence number. And so now the sequence next variable will be set again. So we have achieved what we set out to do, is set the sequence next and the urgent pointer at different times, so the connection between them is broken. Eventually now we will get a ACK, a SYN ACK, and an ACK, and now we've completed the 5-way handshake with these two variables unconnected to each other. If we go back to this equation and we set these values in it, we can see that, again, this line will underflow. And once it underflows, again, the length will be cast to an unsigned integer, and the receive call from any server application that calls receive in the TCP socket will cause an out-of-bounds copy. When you look on both of these vulnerabilities together, they actually impact all VxWorks versions from 6.5 up to the last version released last week, or beginning of July, actually. Okay, so there are two RCEs in the TCP implementation. What can an attacker do using these specific vulnerabilities? So there is actually an interesting use case for this. Let's consider this example. We have a printer connecting outbound to a Google Cloud printing service. And first of all, it goes out to a DNS server, says what is the IP of Google Cloud. That will resolve, and then a TLS connection will be created between the printer and the Google Cloud. So this connection is secure connection, and because the TLS is encrypted, that connection is secured. But the TCP header is actually non-encrypted. And the vulnerability we found is in the parsing of the TCP header. So if we have an attacker here that has some control of the DNS server in this example, then he can be a man in the middle on this connection to the Google Cloud printer. He can say, I am the Google Cloud IP, and so the TLS connection would be going out to his IP. And now, because again, the vulnerability is in the TCP header, he can change the packet going back from the attacker to the printer. For example, turn on this urgent 0 scenario, and that will exploit the vulnerability on the printer, even if it's behind a NAT, even if it's secured behind a NAT. So this is a very unique example of a device behind a NAT that you can attack from the internet. Again, without needing to breach the network at all. Okay, so this was the TCP urgent, and now we're going to talk about the patient monitor that we have here just a bit, and Dory will walk you through it.
Okay, so we had a lot of fun researching all of these vulnerabilities, and we wanted to find some devices to exploit them on. This is one interesting case. This is a patient monitor, a bedside hospital patient monitor, and he has a very unique set of qualities. First, it runs VxWorks 6.6, which makes it vulnerable to the urgent 0 variant that we found. And it has a listening TCP server that receives to a buffer that is allocated on the heap. That is great because most of the devices that we've seen receives on the stack, so we can get away with a simple stack overflow, but in this case we need to exploit the heap, which is interesting to us because we haven't done it yet. And the most important quality that it has is when you Google patient monitor VxWorks, it's the first result and you can buy it on eBay. So I'm going to take you to the 3 easy steps in order to obtaining the firmware for this device. First, you find it on eBay and you convince the shipper to send it to Israel. Then you convince your local FDA that you don't need an import license to buy a patient monitor. And once you've done all that, you can open it up and spot a PowerPC JTAG header in it and just dump the firmware. And once we did that, we were not surprised to see that there is no implementation of security and exploit mitigations whatsoever. There is no data execution prevention here, which is supported by VxWorks by turned off. There is no ASLR, and there is no kernel user separation. This is not uncommon in this type of devices. Most of the devices that we've seen implement no security feature whatsoever, which makes exploiting this kind of bugs really, really easy. So this, as I mentioned, it has a TCP port that is listening and receives to a buffer on the heap, which means that we're gonna need to exploit the heap. This was a good opportunity for us to understand how exactly VxWorks heap works and what are the security implications of it. Okay, so as you can imagine, VxWorks heap is a pretty trivial heap. No security features are implemented here whatsoever. You have a contiguous memory buffer, which is the heap. You have allocated chunks and free chunks, and every chunk holds their own metadata at the start of the buffer. In case of the allocated chunks, you have the 2 size D words at the start. You have them also in the free chunk. And right after, you have the mem_part pointer. The mem_part pointer is a pointer to a global struct that describes the heap. But because, as I mentioned, there is no ASLR here, we can predict it every time. So no problem there. And also, we have the head guard, which is supposed to be, I guess, some more security or reliability feature on the heap, but it is determining compilation time of VxWorks, so not much of a security feature, maybe more of a reliability one. In case of the free chunk, you have the same size parameters, but you have a couple of interesting pointers right there, which are the pointers that put the free chunk inside of the heap free list. So what is a heap free list? Basically, it's just a list of doubly linked heap chunks. And every time a user tries to allocate a chunk, the allocator iterates through all of the free chunks and tries to find the one that is right-sized for the user to allocate. Once it did that, it needs to unlink the free chunk from the free list and then set it as an allocated chunk. This happens in a very trivial code inside of the allocator. You might have seen this code on your computer science assignments. This is the basic unlinking of a doubly linked list without any safe unlinking implemented here. Just the previous chunk next is my next and so on. This is pretty trivially exploited when you can overflow those 2 pointers. And this is called a mirrored write primitive, meaning that once we overflow them with 2 values that are addressable and also meaningful values, we can create a mirrored write, meaning that one pointer will be written to another and in reverse with some offset between them. So what is our heap exploitation strategy? First, we are overflowing from obviously an allocated heap chunk and hoping to hit a free heap chunk. In this specific case, the statistic were in our favor, so no heap massaging or whatsoever was needed here. We just overflow from our heap chunk right to a free heap chunk and then set those 2 pointers in order to achieve our mirrored write primitive. Then we wait for someone to allocate this buffer. This happens quite oftenly on the system that buffers get allocated and freed all the time. So now we have our mirrored write and we can write whatever we want, wherever we want. So remember the struct that I told you that describes the heap? It has some interesting function pointers in it. These function pointers are pointers that hooks all the allocation and free functions inside of the memory allocator. And basically we just steal one of them to get execution time, and also we can execute code before another allocation occurs or another free occurs, so the heap will remain intact and we will not destroy anything yet. So once we get some runtime, we will just freeze this region of the heap. We just hook every allocation and every free call that is happening on the system. And if someone tries to allocate a buffer from our area that we have destroyed, we just ignore that. And if it tries to free, we just ignore that too. And in the case of an allocation, we just give it another chunk from another place on the heap. We also have a primitive that sets a specific data buffer in the data section to values that we control. We won't talk about it, but as I mentioned, there are no dep here, so executing data is pretty easy. And now I'm going to set up the live demo, and hopefully, if we pray to the demo god, it will work.
Yeah. Can we switch to the camera under the table? So this is a magic box, but there is a patient monitor under here just for the, it reflects too much for the light, so we put it like this, and I can connect myself.
Yes.
Okay. So before door starts, this is a patient monitor, like I said, a hospital bedside patient monitor, and it can connect to multiple vital readings, the pulse, the oxygen, and the ECG electrodes, which I won't stick to myself, but actually do work. And we already run the exploit just before the talk, so it's like ready. And this device actually has a built-in debugger, the regular like VxWorks debugger that is turned off by default, but once you run code on it, you can turn on that debugger, and that can be your backdoor to control it various ways. And what we did is upload some code that will allow us to change the vital readings and do all kind of stuff. So for example, we can change the pulse rating of me and the oxygen levels. You can see that I'm not really that excited to see all of you folks. It's just the monitor says otherwise. And now I'm not dead as well, I'm pretty much alive. Okay, so we've done that. We can also put whatever we want on the screen. For example, this Black Hat logo. And last thing, like last night, just before going to sleep, I really wanted to see maybe we can like run Doom on this patient monitor. And I didn't have time to actually do it, but I was able to render one frame of Doom on the patient monitor. And maybe until like the next year, maybe I can actually do Doom completely. Okay, so that was the patient monitor. And now, if that also works, we can take some questions. Oh, actually, I do want to summarize a bit the takeaways, and then we'll do the questions. Okay, so we went through a lot of material. Again, very long research with many vulnerabilities in it. I think I just want to go back to a few takeaways from this talk. First, real-time operating systems, I think, need to get much more attention from the research community. We From this example, we saw 2 billion devices running on VxWorks, but only 13 vulnerabilities found in the last 13 years. So there is much more work to be done in researching real-time operating systems, especially the ones that are so widely used. Second, we also noticed in this research all these esoteric features from TCP IP stacks that are in practice are not used. The urgent pointers, the reverse ARP, these stuff are not used in practice, but are still implemented in various stacks and create an attack surface that is really not needed. So steps to phase out these specific mechanisms is also needed, I think, both in the stacks and possibly as well in the RFCs. Like a new RFC can come along and state no more urgent pointer. And lastly, I do think that this research also shows the challenge of actually finding devices that run VxWorks. So if you would be a researcher for Android or Windows, you can buy an Android phone and you can research it, and it's quite easy. If you want to research VxWorks, you need to find out what is the device that runs VxWorks that I can actually use for my research. It's not an easy task to do. There are many devices that run VxWorks, but it's not an advertised operating system. And it's not something that you go to the store and say, I want to buy a VxWorks device. So there is a challenge in identifying what is this underlying operating system used by many devices, many real-time operating system-based devices. I think this challenge also needs, we need to confront it in order to understand the attack surface of many of the devices that surround us. And we do have 10 minutes, surprisingly, so if you have any questions, there are 3 mics here. You're welcome to. Yeah, go ahead.
Thank you. So I've done a lot with IoT, SCADA, ICE. It seems to be kind of a focus of your company. I'm frankly surprised you only found 13 or 14 that you don't have more.
No, there was also 11, and there was also 13. So
right. I'm surprised you only found 11. Have you done much with fragmentation, like the Rose attack, or any kind of TCP/IP fragmentation? There was another one that came out recently to basically DDoS these devices and just shut them down.
So I'll repeat the question, telling me if you're. So you're asking if fragmentation in TCP and IP can cause denial of service on these types of, yeah. So we did actually look at this, the implementation of fragmentation, and we didn't find out anything concrete about this, but it is a good target for research. Fragmentation in both IP and TCP can cause implementation bugs, not in this instance though.
Look up the Rose attack.
What again?
Rose attack, it's online.
Oh, yeah, like I mentioned, I think before, there are many vulnerabilities that cause like resource exhaustion, denial of service in the application layer. But getting it to denial of service that actually reboots the device or causes remote code execution, that's another type of attack.
Thank you.
Sure.
Yeah, thanks for the presentation. Really interesting work. At the beginning of the presentation, you mentioned that the same TCP/IP stack is used in ThreatX. Did you guys also investigate to see if you could accomplish these same exploits in ThreatX?
So we haven't. Actually, what we understood from Wind River, which is now owns IPNET, is that since 2006, when they purchased IPNET, these other real-time operating systems no longer use IPNET. But it is something to consider, yeah.
He just stole my question.
Yeah.
Would control for integrity block your exploits attempt?
Can you come in?
Would control flow integrity block your exploits?
Oh, well, that's really not something that exists in VxWorks devices. I think there are much basic stuff that can prevent these attacks from being such easy to exploit. The door mentions this, no ASLR, no DEP, no stack canaries. They're not implemented in practice in many of VxWorks-based devices. And if you will add another mitigation to that, it will help even more.